Hello Math 3 to 11 students, here's lesson 15, Introduction to Cryptography. Or is it better to call it an appendix? I don't know, I'm not sure. In any case, here we go. Introduction to Cryptography. Let's begin section 1, Classical Examples and History. Let's begin with the simplest and the oldest example. Shift cipher. Mathematically, it goes like this. Just addition modulo m. And early historical examples include communications between Julius Caesar and Marcus Cicero around 50 BC. And our textbook author calls it Caesar cipher. And I checked other textbooks too, and they all call it Caesar cipher, so I think it's a widely accepted name. After all, Julius Caesar is a famous person, so is Cicero, and this communication actually survived. You see, what's the purpose of cryptography? It's for secrecy. So most of the time, the encrypted message is torn apart and destroyed. It's very rare they survived. But in this case, it did, thankfully for us. Basically, we do this. Add 3, in other words, shift the positions of all those letters of the alphabet by 3 units. And then if you shift those back 3 units, then you're going to get the original message like this. Of course, this is not the original message. It's not in Latin, as you can see. It's in English. I got it from the textbook, not from the original letter from Caesar to Cicero. Meet you in the park, it's in English, and then apply this plus 3 modulo 26. And of course, we are using modulo 26 because there are 26 letters in English alphabet. For other European languages, the modulus may have to be changed a little bit. And if you include all those punctuations as well, then it will have to increase even further. Let's keep it simple, just 26 alphabets and then disregard the space. Meet you in the park, M becomes N or P, so it becomes P, 3 spaces, and E becomes FGH, so it becomes H, and then another H. And then look at this Y, it becomes Z, and then back to A, and then B, so we have this. You see, plus 3 modulo 26, etc., etc., and we have this kind of digit string, or string of alphabets rather. This is an example of shift cipher. In general, it is, as you can see here, n plus k mod m, and then n minus k mod m. The original map that shuffles up the alphabet is encryption, and the inverse map is the decryption. So apply the inverse, then you get the encrypted message back into the original so that you can read. And then the encryption and decryption maps come with some parameters, which we called the key. In this case, k is the key value. And in this particular case, the k value is 3. So plus 3 and then minus 3. So it's a simple system, easy to understand, but there's a problem. This encryption can be easily broken, really easily broken. It takes only 26 tries. If you know if this is a shift cipher, and it's not too difficult to tell whether this is shift cipher, you can apply statistical analysis. You see, there are far more consonants than verbs. And consequently, we have far more vowels than consonants, excuse me, not verbs. What I meant is vowel. Like this, E, there are 3 E's already in this short sentence, and O and U are also vowels. And then look at this encrypted message. How many H's showing up here? Already 3. So that already rings a bell. This could very well be a vowel. And if you have HH showing up, it's highly probable we are looking at either EE or OO, because the other repetitions are not very The other repetitions are far rarer. I mean, AA, II, UU, those do not appear very often. Of course, those could be TT or something like those, but, well, T's appear common very often, but not as much as vowels. Anyway, through statistical analysis and trial and error, you can easily break shift cipher. So this may have some historical importance, but otherwise this is unusable. The reason this is not very good is because this cipher system is monoalphabetic. Each letter in the alphabet is mapped onto one and only one letter in the alphabet. For example, E is mapped onto H. H goes back to E, vice versa. There's one-to-one correspondence. So those kind of cipher systems are always vulnerable against statistical analysis. Now, what if you make it a bit safer by trying multiple letters or multiple numbers to E? Instead of going modulo 26, increase the modulus far bigger, say modulo 100. And then use Scrabble system. Remember Scrabble game? There are 12 E's. So 12 numbers are assigned to E. And then there are 9 A's. So 9 numbers are assigned to A. And then how many P's? For example, I think there are 2 P's. And then only 1 K, 4 R's, and then 2 H's, and then 4 T's. Kind of like those. 4 T's, maybe 6 T's. Oh, I'm not so sure. And in any case, you can adjust the frequency like that so that you can tear apart the statistical analysis. But this is big but. There's a huge problem for that. The key must be simple, because the messenger has to take the message from Caesar to Cicero, and then the messenger has to tell Cicero the key. Key is 3. And he has to memorize it. If this key is part of the message, then it'll completely destroy the purpose of cryptography. And if the key is so complicated that it has to be written down, and if that's lost or even worse, stolen, then this entire system becomes useless. So key has to be simple. And that's something one has to memorize. And after using, never write down anywhere. And then everything, especially the encrypted letter, must be destroyed. So if you have really complicated key, what number to what number is A, what number and what number are B, kind of like that, that'll completely destroy the purpose of this cryptography. So you can't use it. You have to do something better. How? Well, let's make it a little bit more complicated and make it an affine cipher by introducing another key. Instead of just using plus K, here just plus B, we have multiplication as well, so that we have AN plus B. So the inverse map, or the decryption, is N minus B divided by A. And when can we divide? Of course, A and M are relatively prime. In that case, the multiplicative inverse exists, and the easiest way usually is to take A as a prime number. Then most of the time you don't really have to worry about anything. So that way you can set up a encryption and decryption through 2 keys. And this kind of system is called affine cipher, because this map here, G of N, this is an example of an affine map. Multiplication and then addition. If you drop the addition, this kind of map is called a linear map. Linear map plus something, that's called affine map. Here's an example. Okay, this time I didn't use the example from the textbook. I used my name. Okay, Ike Kang, and I is 9th alphabet, K is 11th alphabet, and so on. And then let's use this map, 7n plus 10, and 7 and 26 are relatively prime. That's easy to see because 7 is a prime number. And then the multiplicative inverse of 7 turns out to be 15. Okay, please check. So that the decryption map, the inverse map, is 15 times n minus 10. Okay, let's apply this map. 7 times 9 plus 10, so 7 times 9, 63, plus 10, 73. That turns out to be 21 plus 26, and so on and so forth. And then rewrite these digit string into alphabet, then you get this UIS, and then there was a space there, keep the space, and so on and so forth. We get a little bit more complicated system here, and then we have 2 keys. So each has maximum 26 choices, so 26 by 26. So 676 choices. So it's not as easy to break, but still 676. For one person it might take a while, but for a group of a team of code breakers, it's easy. This is also vulnerable against statistical analysis because this is also monoalphabetic. Each letter in the alphabet, each character in the alphabet is mapped to one and only one letter in the alphabet. So if you have a long message, then typical vowels such as A and E and O will show up a lot, so you can backtrace and then narrow down quite further, and then eventually you'll be able to break those keys. There are not that many to begin with. So this too is not very useful, and for messages it's totally useless. But do not count out the affine cipher completely. It may not be useful for encrypting messages, letters, or documents, but it's quite useful encrypting images. How do you get a digital signal of images? You get the pixels, and then the position of the pixel is given by XY coordinate, and then you have color information, red, green, and blue. Let's forget about this color information, just go black and white. So we have XY coordinate, and those are integers, and then we can apply the affine cipher to X coordinate and then Y coordinate. And then here's a little bit of tricky part. This even though we have mod m, re-express those as decimal expansions, and then express those mod 1 eventually, then we end up with a chaotic map. So even with computers, it's hard to break, to tell the truth. So for image processing, the encryption of image processing, this affine cipher is actually quite useful, and some version of it is currently in use, as a matter of fact. If you are interested, go ahead and look for Arnold cat map or things like those. As a matter of fact, my specialty in research is close to this, as a matter of fact. And those 2 examples are both monoalphabetic ciphers. So for images, okay, that's another use, but for classical use of cryptography, encrypting messages, encrypting some letters, some words, some sentences, they're not really useful. So in the next video, we're going to talk about a little bit more recent example. Recent, I mean by sometime in 15th century, 16th century kind of thing. Alright, see you soon.